Good morning, class. I hope you had a wonderful vacation, stay home vacation. And today we're going to conclude our lecture on conservation of motion by practicing on conservation of energy. And then you're going to have a whole week of reviewing and practicing, and we're going to have a test next Wednesday. Okay? So, conservation of energy. We talk about energy. And frankly, we talked about conservation of energy before. So recall that before, like a week ago, we learned the potential energy, kinetic energy. So potential energy is the energy that will convert to motion potentially gained by the height. Basically, it's one type of potential energy is the gravitational potential energy. That is the potential energy we talk about most of the time. So the formula is PE equal mgh, the mass, the gravity, and the height. And then we have kinetic energy. The kinetic energy is the energy that drives the object into motion. So our formula for kinetic energy is Ke equal half mv squared. Of course, you need all those formula on your test, and I'm going to give you a list of the formula you're going to use. Okay. So, and also before the energy, we talk about momentum. Momentum is conserved in a closed system. So is energy. And we keep talking about, okay, energy cannot be destroyed or created in a closed system, right? So, for example, we keep talking about roller coaster, and I hope you watch the roller coaster of physics, the video on YouTube. It's fun. Make sure you watch all those three video I post in Google Classroom. It will help you understand a lot more about the concept. So, in a closed system, when we look at the roller coaster, remember when you go up the roller coaster, it's very slow, and you hear the machine is driving you up. So you are gaining potential energy when you go up. And when you reach the highest point, and it's pretty much free fall from there. And the reason why you can go back and forth and go into loop is because the potential energy when you at highest point is slowly convert to kinetic energy. And then when you reach the lowest point, and all the energy convert to kinetic. And that kinetic energy can drive the roller coaster, the cart, all the way back up. So in a closed system without other factor outside the system, the energy or the momentum, all that, they're conserved. So throughout the ride of roller coaster, it always gonna have the same amount of total kinetic. I mean, same amount of energy. And here, the energy when we talk about is basically the kinetic energy and the potential energy. So the sum of kinetic energy and the potential energy of the object is often called mechanical energy, and that's the energy we often talk about that is conserved in any kind of motion or roller coaster here. So I'm just gonna go ahead and to work on some practice problem. Okay. Please read through the whole lecture, even though I didn't go over them. But after read it through one time yourself, you'll gain so much better understanding just by, imagine it. So, example word problem number one. Suppose a cannon is sitting on top of a 50-meter high hill. So, when we see 50, obviously there will be this is height, right? And a 5 kilogram cannonball, this is mass, and that will be potential energy. Okay? The potential energy is mgh. And then that cannonball is fired with a velocity of 30 meters per second. So 30 meters per second is v at some unknown angle. What is the velocity of the cannonball when it strikes the earth? So and then the kinetic energy here, Ke, since we have velocity, so Ke is half mv squared. Okay. Since the angle at which the cannonball is fired is unknown, we cannot use the equation from projectile motion, go for us. However, at the moment the cannonball is fired, it has a certain kinetic energy due to the mass of the ball because it has the initial velocity, right? And also it has a potential energy due to its height. Those two quality of energy can be calculated when the ball returned to the earth. The potential energy will be zero, therefore its kinetic energy at that point must account for total of its original PE plus KE. So basically what it means is if you're going to use a formal equation, so the potential energy initial, okay, that's I, plus kinetic energy initial, okay, initial, equal to final potential energy F plus final kinetic energy. Okay, that actually makes sense, right? Because the total amount of energy, initial total amount of energy, never change. So the initial total amount of energy should equivalent to the total amount of final energy. And then we know the mechanical energy here we're talking about is always potential energy with kinetic energy. So our initial potential energy is mgh, right? mg initial height. Our initial height is 50 meters per second. 50 meters. Plus initial kinetic energy is half m initial velocity, which is 30, mvi squared, equal to final potential energy mgh final. Since it struck the ground, so the final height will be 0 plus final kinetic energy, half mv final square. But the v final is the final velocity we're looking at, which is the question mark. Okay, so now all we have to do is plug in number. Since my pen is not working properly, so I'm just gonna underline the number that's changed, and then you can plug in the number that it's the same. Okay, so initial height is 50 meter, and then initial velocity is 30 meter per second. Okay, and then your final height is 0 meter, and then your final VF is, let's say, X. All right, now you plug the number and then you use a calculator to calculate it, and you can find your answer. All right? So it's always going to be like that. The initial total energy equal to the final total amount of energy. Ooh, shoot. Why did I? Okay. Anyways. All right. So example number 2. Example number 2 is the same thing, right? A 2-gram bullet moving at 705 meter per second strike a 0.25 kilogram block of wood at rest on a frictionless surface. The bullet sticks in the wood and the combined mass moves slowly down the table. So when you first look at it, it actually there's many things you can do, of course. First of all, it's a collision. It's a inelastic collision because they stick together and move together, right? There's deformation. And then, of course, the energy is conserved and momentum is conserved. So this question is actually broken down into 3 different parts. Let's take a look. All right, let's just write our given. I'm just going to underline it. This is the mass of the bullet, M1, okay? But you have to convert that to kilogram. Remember? Okay. And then this is our initial velocity of the bullet, okay? And then this is the mass of the block. This is M2. At rest, so initial velocity of the block is 0. And then they strike together and move slowly together. So what is the kinetic energy of the bullet before the collision? So we're only looking at kinetic energy of the bullet before it hits the block. We know the kinetic energy is half mv squared. Half times the mass of the bullet. See, you have to convert that to kilogram. And then multiply the initial velocity, become 497 joule. And that is your energy, right? Part B. What is the speed of the combination of the collision? So that actually requires us to look at the conservation of momentum, and we have this kind of practice before. Remember, initial momentum is equal to final momentum. Initial energy is equal to final energy, right? So if you look at here, it actually used the momentum formula, conservation of momentum, to solve this problem. You see here? More precisely, it really should be the mass of the bullet times velocity of the bullet. Ooh, let me use small. I use a small one. They use the capitalized. So that's the momentum of the bullet times mass of the wood and velocity of the wood. Okay, velocity of the wood, which is the momentum of the wood before collision, equal to, since they stick together, so your mass of the bullet plus your mass of the wood times your new velocity, final velocity. So this is momentum before collision. So before should equal to momentum after collision. After. So everything else is given to you. All you need to look for is that V final. All right. Okay, the last part. The last part is how much kinetic energy was lost in the collision. So kinetic energy combined is still half mv squared, right? So we find our V final, and then we can find our kinetic energy after collision. So kinetic energy after collision is still half mv squared. So half m is the combination of m bullet plus m wood, right? And times your final velocity and give your final kinetic energy. And then kinetic energy before, subtract kinetic energy after is the how much energy you lost in a system. All right. Okay, so this type of problem, we did some of them when we practice on conservation of momentum. So the concept are very similar, and then the formula is what we are familiar with. You just have to choose which formula to use. So go ahead and do your homework on conservation of energy. I post in homework file and practice on those. And also, our test is on Wednesday. I have posted a link of practice test review on your Google Classroom. The file, the name of the file literally says conservation of motion test review. Okay? And it will show you the solution, it will show you the correct answer when you put the number in. However, you know my style. I'm going to give you the same problem, but give you a different number. And then you have limited amount of time to do your test, which will be 2 hours. And I'll give you 20 questions. So you don't have the time to go back and forth. We are going to spend the rest of the week and the beginning of next week to review the entire test. Make sure you do some practice before we review and make sure you attend the Zoom meeting. Okay? All right. I'll see you soon. Have a nice day.